So last week I put out a LinkedIn post on the topic of the carbon footprint of an email. Not only did I put out the post, I also set up a hacky contraption to try and measure the effect the email has. It was pretty straightforward, simply measuring the traffic on the router, which has been disconnected for everything apart from a wired portion of the network, which would then send several emails just to see what the effect would be. And it was measured on an oscilloscope. The total energy consumption didn't change, but a lot of people mistook that for email taking no energy. I then put out a subsequent video to explain clock cycles and why clock cycles are running anyway. And the arguments continued. But it dawned on me at one point in that debate that maybe people don't really understand the difference between modeling and accounting. There's a big focus on carbon accounting at the moment. Quite rightly, because people have to be able to measure the footprints that they have. The trouble is when you use an accounting process for a modeling context, the answer is never correct. And the reason for that is actually more fundamental than anything to do with climate change or any other such topic. It's because of the fact that when you account for something, that is a description of the state of an organization or a carbon subject, i.e. something you're studying, at a particular moment in time. And doctors and anybody who studied in the medical profession or people who have studied statistics understand the difference between two types of statistics in that particular case. What's called descriptive statistics, and the other is inferential. There is a fundamental reality about these two, and that is descriptive statistics can only ever be looked at in retrospect. However, a number of different errors in our society generally come about as a result of this misunderstanding. Descriptive statistics do not represent the space that inferential statistics work in well at all. So in the event that these two situations are not the same, you will, applying this tool, will screw up context around this. And we saw this in the public health response to the pandemic, where people were trying to use descriptive statistics, especially even people on stage, people who should know better. People were trying to use descriptive statistics to try and reason in inferential cases. And one example of where that might be problematic is when you have frequentist statistics. That's the typical stuff that you're taught in GCSE, A-level, and obviously most undergraduate degree courses which aren't statistics based. You'll often be taught descriptive stats. So anytime you're talking about basic random normal distributions, for example, then all of those cases are actually based or founded rather in the principles of frequentist statistics, i.e. how often an event actually occurs, or how often or how many times rather will you see a particular phenomenon occur in society. Inferential statistics is fundamentally different because this world is not frequentist. So I'm going to write these two here, and probably in a different color, right? While this, best case, is Bayesian. And because this uses current events to update, if you like, its a priori assumptions about stuff, you can start with this in this world and update it with knowledge that you go as you go along. This makes an assumption that never changes. And this has problems in a lot of different ways. One of the most obvious ones is this number, or you might know it as this. Or if you're used to other contexts, especially common contexts, you will probably know this as people talk about it as the R rate. Now, the R rate obviously is within a pandemic is the reproduction rate. But the problem with that reproduction rate is it's an equivalent rate, right? And that's why it's called RE. The E stands for equivalent. And the idea of that is in any population, so let's suppose you pass it on to two more people and two more people pass to another two more people, right? Supposing, to start with, then the rate or the equivalent transmission rate, or reproduction rate as it's often known as, is, in this case, 2. Right? The R rate would be 2. You pass it to every 2 other people. That's fine. But that's an equivalent. And there's a couple of reasons for that, for the fact that it's only regarded as an equivalent. The first one is the fact that you might not know 2 people. You might only know 1 person, while someone else might know 3. So that's the first problem. The second one is that in an unvaccinated population, right, and who are receiving the virus for the first time, the entire population is available to the virus to be infected. And that rate is what's known as R0 or R0, right? So as soon as it hits the ground, nobody's vaccinated, nobody's got any immunity whatsoever. R0 is the is the reproduction rate for the entire population. Now, that's useful, right? And at the very, very beginning, at t equals 0, these two are equivalent, right? That means as soon as it hits. But obviously, over time, once you've been infected, let's suppose we now infect this person, and you infect this person, let's say. And as a result, they infect that one person. And let's suppose you now infect this person, right? Because they've got it through this line, say. What you now have is your reproduction rate actually, at some point in time, actually doesn't stay static. So what you'll notice is that although R0 has never changed, right, your RE in this scenario has. And the reason for that is because if you now infect this population of people, this population here, and you reinfect them, or they get infected through another line, this person can only pass on to one other person. Right? Because the other people have now got some immunity from that. And as a result of that, your R0 and RE are not the same anymore. However, if you are constantly evaluating the environment based upon just your knowledge of R0, because that's your past historical understanding of it, your current understanding will always be out of date. And this is the difference between an accounting and an inferential position. Well, it's part of the difference between an accounting and an inferential position. You initially had a position where these two numbers were equal in an uninfected population, but something has happened in the current context that has now made these two unequal again. And this is the same in any form of accounting versus modeling position. So let's now go back to talking about accounting and modeling. And the reason why is I want to touch on the concept of an effective theory. Now, this is a concept actually Stephen Hawking talked about a lot. And an effective theory is only as good as its appropriateness in the context in which you want to use it. So, for example, when you were in school, you probably studied trajectories. So that means you throw a ball, it will follow a particular path. Right? This ball has a force down due to gravity, and at the same time it also has velocity components that take it upwards at a particular rate, and it takes it across at a particular rate. And when you look at these two individually, they often used to tell you that this bit here had an acceleration force associated with it and this one didn't. So if you were to take a look at these two numbers, they would be equal to 0. Well, it would be equal to the component at a particular velocity, which we'll call y0, and it's having a certain amount of force applied downwards on it, which is an acceleration times by whatever time it is in that journey, because each of those little increments that you've got here is effectively a time increment as well. And that x can also be a time increment, and that y can be a time increment, which is one of the reasons why these are effectively differentials. And that means that when you take the second derivative of this, right, you're looking for what is ultimately, that's a constant, and that of course you differentiate, which then gives you minus a, which is equal to minus g when it's only working with a point mass. So that's your effective acceleration. Then gives you a useful position to then look at an accounting question. So let me give you an example. So accounting question will ask something like, how high, try that again, did it go? Right? And to do that, you then say, okay, well, if I look at that, I would start from this position knowing that that's true. We know that this is the basic equation, and of course, and at this point, your total velocity is 0, which means that taking a look at that y component, we would expect this to equal AT, right? Because you're starting from the position where that will then equal 0. And to calculate that particular, the total height, you then first of all find the point at which velocity would be 0, which effectively would mean solving this equation. So if you know whatever your initial velocity was, you can then find the time by simply doing that. Right? Great. The next step, of course, would then be to say, okay, well, now that I know the time at which this was 0, and I know that initial velocity, I can start calculating the total distance y based upon equals u squared plus 2as. All right, so rearranging that equation, you get yourself v squared minus u squared over 2a, right, where that's the acceleration, which then gives you a position where you can say, okay, well, now that I know that I've got these two values, I know what my start velocity was, I know what my end velocity was, the end velocity would have been 0. That leaves you in a position where you've got minus y0 squared, right, over 2 times by your acceleration due to gravity, which is minus g. Right? And that'll give you a total effective distance traveled. So that then gives, you're set. That's your particular point where it's traveled. You can now answer that vertical question. Right? Another question it might ask is how horizontal did it go? Right? And you just do the same again. Okay, well, that means if the time itself was this, you just plug this guy or this one into the equation you had for this, and that's job done as well. That's all very well. But we've done a few things here that actually are useful in the model, but the account doesn't have that information in it. And the reason why that's important is because if we start to look at what the account has actually given us, all we have is a knowledge about a ball or a projectile of some sort and how far it is from the ground. That's all the account has told us. And if you also look at this another way, to get the information about this account, we actually didn't really need to know anything about the horizontal travel at all, right? Because our concentration to answer this question was simply through this portion of stuff. So an effective theory for this would simply neglect the horizontal position, because you actually haven't traveled side to side. You only asked the question about the height, right? You could ignore, right, the horizontal axis completely. We didn't care about that. So to answer the question on that effective theory, or of that account rather, it's sufficient as an effective theory. So to answer this, it's sufficient as an effective theory just to talk about the height, right? Just to care about this part of the equation, right? Nothing else at all. But the trouble is, until you go and look at the actual trajectory that this thing has taken, specifically this curve, right, you don't actually know the total energy that you've thrown into that system, right? You know that there's a component that goes up, but there's certainly no component going sideways, because all that happens here at this point is answered by what happens only in this component. So that's the difference between an effective theory and an actual position. Now that becomes important because, oops, I'm not sure what I did there. That becomes important because when you want to go to act on something, so for example, if you're seeing that this person is, this thing that's throwing it, or whatever it is using up, let's say, 52 joules of energy to launch this thing, right? You can choose to do one of two things. The first one is you can work with the effective theory and assume that this 52 joules is thrown entirely upwards, because that's all the account is telling you, right? So you assume that 52 joules is thrown upwards. Yep. There's no other energy in the system because it's not going sideways as far as you are concerned based upon the accounts. The other option you have is to go look-see, right? And the key point about going to look is because you'll find that actually the energy is actually not being expanded up and down only. It's being expended, thrown at whatever angle, theta. And that energy is upwards and sideways, right? So there's actually two sets of energy going out there based upon what's being transferred into kinetic energy at that point in time, at the point in time 0. So because of that, you can then say, okay, well, listen, I really only care about how high it went. So you could effectively say, fine, okay, if you only care about how high it went, I'm going to stop throwing things at an angle theta. I'm going to throw it at an angle theta equals 90 degrees, right? Which means that it's only going to go up and down. And what that does is that reduces the energy. Okay, fantastic. Sounds brilliant on paper. But here's the problem. If you view it just as this, right, you are not at all aware of the sidewards motion, the horizontal motion. Because your effective theory, as far as you're concerned, right, you've decided that the effective theory to answer your question is just this, up and down. So I'm going to label this one as effective, right? F, right? And this is your F, right? Effective theory. So because of this, you aren't fully aware of what energy is being put into the system, right? So as a result of that, you might think everything's hunky-dory and accounted for, when actually it isn't. And we see this all the time across economics and economic modeling. And this is not any different in carbon accounting, because carbon accounting is asking these sorts of questions, right? What is my scope emissions, right? So people who are familiar with carbon accounting will be familiar with the idea of scopes, right? Scope 1, 2, and 3 emissions. The trouble is, those are, again, effective theories. They are asking these questions. These are policy accounting positions, right? They don't actually have a resemblance in reality. They are an attempt to create an effective theory for accounting for energy or carbon dioxide. And this creates a problem. And I've said this a few times before, because what you're doing is you're trying to address this to policymakers, and you're also trying to address it to accountants, basically. But to act, you don't have enough information. Because here, in our example, which is looking a bit messy now, that 52 joules that you're expending is actually expended across this curve here, right? As we've seen before. And that means with this visibility, you don't have enough information to actually effectively optimize your process, your energy use, right? But if you were to act on this, you'll say, okay, well, I need to find another way to throw something that doesn't, say, use 52 joules. The reality is that doesn't change. And the reason why is the ball has a particular mass and the height has a particular distance. The only thing you can do is choose where you get your energy from, right? If you model it, on the other hand, and you understand how the system works, let's do that in blue. If you understand how this system works and you have the necessary knowledge about these other elements, what you get is a fundamentally greater understanding of not just the system statics, which are often measured by these accounting questions, right? There's just the statics of the system. What does it look like at rest? But also the dynamics of how it works. And that latter piece is by far the most important position on it, because that gives you an understanding of how that changes at time t, at any time t. So this then means that you can look at the climate and any carbon intensive environment that you have, energy, any place where you're using energy, and you can start to find the links between systemic components when you understand the dynamical portions of it. You can understand what the accounts look like at each individual state if you wanted to, fine, but actually that only gives you the statics. What you don't know from that view is how the system dynamics change when this node here, or this link in the chain, changes relative to this node here. And this gives us a bit of an issue, because anything that then tries to reduce this system to a series of averages that can be applied on an individual basis is actually making a fundamental mathematical mistake, because it is using a process of descriptive statistics to try and reason in inferential spaces. So if you take the average of a human footprint, for example, and then try to apply it in other spaces, you're going to get it fundamentally wrong. And in the case of emails, that's exactly what's happening. it has been reduced to an average number per email, which actually doesn't have any of the necessary modeling behind it to determine how the dynamics of it will change. And this is where we live in these two separate worlds of carbon accounting and carbon modeling. And I joke, as someone who oversees a mathematician, accounting math isn't mathematics. It's actually just a summation at a static point in time. And those statics aren't sufficient to create a full system understanding, because you have to have the two components of statics and dynamics to do, or to understand any system. And to illustrate this, I'm going to try and use this other analogy. And it's a pretty straightforward one. Most people who are interested in the climate will be very aware of this. And we're going to go back to looking at lorries. So in total, this lorry is equal to 28 tons. Right? And that's right, the lorry itself weighs more than the load. Not only that, typically this lorry will emit around about 190 grams of CO2 per ton per kilometer. Okay? So that means on a 28-ton lorry with its load and everything and the driver will emit 5.3 kilograms of CO2 per kilometer. And let's say the average distance is 100 kilometers. Right? Total distance is 100 kilometers. That would then imply it's coming out at 530 kilograms of CO2 in total. So people think, oh my God, I really need to reduce my carbon footprint. And they're right to reduce the carbon footprint. That's not really the issue. It's the fact that they are choosing the wrong tools. And I'm going to prove that now just by looking at this simple example. So let's suppose Joe Blogg says, I buy X amount of stuff and I need to halve it. The assumption they make in the accounting world, if you like, is that halving that will halve the emissions ultimately. So they think, okay, well, if I halve the amount of stuff, I'm only spending 95 grams of CO2 per ton per kilometer. No, that doesn't happen, because that's per ton per kilometer, right? So these two here are defined by constants. Therefore, this number effectively can't change unless you can fundamentally change the truck, right? If you change the truck, that can change. Another mistake they make on the accounting side is they make an assumption that the total that they buy is the assumption that they can halve that by halving the weight. So if I only buy half my stuff, then I should get 14 tons of stuff only, and that means I get less per load. No. And the reason why that's the case is because there's for two reasons, in fact. The first one is that makes the assumption that a lorry will then drive around with only 14 tons in total. And we already know fundamentally that the lorry cab alone is what this bit here actually weighs 18 tons, right? So that's false, because that's also an impossibility. But the accounting makes the assumption that this is possible, because that effective theory is that everything is an average, and therefore you can simply multiply all the numbers out, and therefore if you want to act on it, you simply halve those numbers. That doesn't work. So you can see here that is an impossible thing. You certainly can't reach that possibility without then changing the truck. This is wrong, and this is wrong. Right? But those incorrect assumptions, that misinformation, that misunderstanding, comes from the fact you try to use accounting to do the job of a model. That doesn't work. And this is one of the reasons why mathematicians are frustrated with normal accountants, as in financial accountants, because they will often go around the houses to do something which can actually be calculated in very few mathematical steps. Or what's worse is they don't have visibility of the full dynamics of the organization, because they are only ever looking at accounts at certain moments in time. The reality is that if you yourself chose to halve your consumption, the only thing you will ever do is affect this 10 tons. So let's suppose everybody did that. What will actually happen? This 10-ton trailer, right, will actually now say weigh 4 tons. We'll give it a couple of tons for the size of and the weight of the trailer itself. So that's now the actual effect that you can have in this case. In reality, let's click the green one. Is you can only ever affect 4 tons of that load, i.e. if you went down to half your consumption. Yep. But there's a problem with that. Unless you fill that truck right? What's the actual emissions going to look like? So a laden truck, that means a full one, emits this. Knowing that you can only affect 4 tons of 28, now you're in a position to start doing a little bit of mathematical modeling on it. And that is that you divide your 4 by 28 and now multiply that by the 190. So what do we get with this? It means the maximum you could affect is 27 grams of CO2 per kilometer. Maximum, right? So you're now in a position where you understand the total effect that you can have on this. But you'll note that even the vast majority, as a result of that, 163 grams, will still continue to be expended. While in the world of accounting, it overestimates the effect that you can have on the carbon footprint. And this is one of the main reasons why most of the reporting at policy level is completely off. We have to take a sharp drop to reach our net zero targets. And the reason why we're not getting there is they are using accounting systems like this, right, here, when they should be using an understanding of this, right? And that's why we're not getting anywhere near the drop in carbon dioxide that we need to see. Nowhere near, because we are making assumptions about or overestimating our ability to deliver the changes that we need, right? Especially by doing fractional stuff. Now, email is worse than that, right? So this is trucks. This is just trucks. This is something very, very tangible. But email is worse than that, and the reason why email is worse is because, as I said in the previous video, which I won't go into again, the clock that synchronizes email across different connections, routers, telecoms, environments, etc., is always running. It's always running. So that means that the energy, whether you use it or not, is expended regardless. What email does is it says, okay, well, I need to send something from A to B, right? So I'm going to take this little thing. Let's pick a color, let's pick blue. I'm going to take this time slice and I'm going to send my packet by starting here, sending a number of bits, getting to a particular point, sending my stop bit, and stopping there. So here's a start, and here's your stop. Right? Over time, at some point in the future. I'm just going to make that clear. So what you have to understand is that whether you use that time slice or not, that time slice is happening. And what people often make the mistake of trying to combine email with how the PC works, right? When it isn't. Email actually doesn't have any meaning in the world of binary, right? Binary bits and bytes, that's on and off switches, are effectively sent regardless. And what's worse with PCs is that they are not like an on-off switch in your home. In your home, you will have a switch, right? Let's try and draw that if I can, right? And that switch, if you switch it down, it disconnects from the circuit, right? So you're like, great. Schematically, that will disconnect and reconnect the circuit, basically. So that comes straight onto the battery with a particular lamp somewhere. Let's put a lamp at the top here. Switch on, consumes energy. Switch off, stops consuming. So you think, okay, well, that must be the same as this. Well, it's not. And the reason for that is because in the computing circuits, these are not driven directly by the switches. What actually happens is that they'll often have a PSU, right, which most people will be familiar with. So in a PC, that PSU will be a power source of some sort. That will then send out the power, and that is coming from the mains, regardless. So you'll often have a 750 watt PSU for a desktop. Out of that comes a series of lines. Some of them are grounded down to 5 volts. The other ones are 12 volts, right? That's on ground there. And that's what's output. Oops. If you then go a step beyond that, these plug into the motherboards and the disks, and those disks are always running. Right? Those disks are powered all the time. So this is a constant voltage. It'll draw current from it, but that's a constant voltage. That's the constant voltage drop. There's nothing you can do about it. And on the motherboard, when it starts to clock on these cycles, as soon as you switch it on, it starts clocking. And that's because on the motherboard, there is a crystal clock oscillator of some sort. And looks something like this. And that oscillates. Typically it's not on the 12 volt line, actually, it's usually on the 5. Let's put it in the right place then. So after that, you'll have a clock oscillator of some sort, and that starts the clock going. And that here is a crystal, and it works because it is powered across, or if there's a voltage drop across it. And that voltage drop has to exist for that clock oscillator to oscillate. So that means you simply can't switch that off. So as soon as you switch that off, that stops oscillating. If that stops oscillating, your computer can't then clock the signals in. And the reason why it does that is because what typically happens in a computer, this is a total crash course, there's more information elsewhere if you need it, is that a CPU, I'm going to do it as a block diagram, has 3 main components to it. One of them, of course, is the power that goes into it. There's then the clock signals, which occur, and then it outputs stuff on control lines, which are often matched to this, data lines, and address lines. And all of them are synchronized by that clock. All right, so these are all synchronized. This, and this are all synchronized by this clock. And that's why they have them in PCs. And that synchronizes everything from the CPU to the RAM to the chipset, etc. And it doesn't just synchronize to these components, it also synchronizes the multiplier as well. For example, it can the CPU might be 2 or 3 times faster than the RAM, for example, and as a result of that, there'll be a buffer somewhere. Often you'll see them as L1 or L2 buffers, layer 1, layer 2, and even layer 3 buffers. Some of them will be built into the CPU, which is one thing, but all of them, again, are controlled by the clock. So every third cycle, it will then write what's in the buffer to the RAM, for example. And all of it, every single part of it is controlled by this clock, right? Because that clock is the central synchronization mechanism on any CPU. Worse still, it's the same on any microcontroller, right? That's the same on any microcontroller. And routers internally are controlled by one of these. So whatever happens, you have a clock that's running all the time. So that hopefully has been a whirlwind tour as to why using accounting models for modeling is wrong. And this has been fundamentally learned by the financial accounting sector, if you like, probably 50, 60, 70 years ago. You cannot use accounting as a mechanism of actually modeling your business. And the same is true of carbon. When you make decisions based upon the carbon account, all you're doing is storing up and creating climate trouble. With that, I'm going to bid you adieu. Thanks very much.